Today we are talking about two things that can save a blast furnace life: hearth care and the smart use of titanium dioxide or TiO₂. The hearth is the most critical zone in the furnace and the least repairable once damaged. We will look at how TiO2 forms protective layer, the numbers we must target, and how this fits into an overall healthcare strategy. The data you will see comes from large scale European projects, Japanese and European operational studies, and a recent industrial trial in China. Now, a blast furnace reline is expensive as this is known to everyone, both in direct cost and in lost production, apart from the distortion in the safety and environmental norms. In Japan, some furnaces have exceeded 10,000 ton per cubic meter of campaign output with 11-13 years between reline. Our challenge is that modern high productivity operation means more molten metal, more tapping cycles, and more heat load at the hearth wall. The main failure mechanism is carbon brick erosion. The molten iron infiltrates, creates a brittle layer, and cracks form. Once that start, erosion can accelerate extremely quickly. When we inject our charged TiO2, it is partially reduced in the furnace to metallic titanium. In the hearth, hot metal titanium combines with carbon and nitrogen to form titanium carbonitride, that is TiCN. Now this TiCN precipitate out when the saturation product of TiC and N in the hot metal is reached. These crystals migrate to cooler hearth wall areas and form a dense hard protective layer. That layer acts like a shield, reducing direct contact between molten iron and carbon brick. From the thermochemical modeling and industrial trials, we know exactly when TiCN will form. The solubility of titanium in hot metal increases with temperature. Silicon helps keep titanium in the hot metal, and with silicon above 0.42%, you get more Ti available for protection. Sulfur does the opposite. Above 0.061%, it drives titanium into slag instead of into the hot metal. Now, from the Chinese industrial trials, the sweet spot for protection is Ti in the hot metal above 0.074%, Ti load between 6 and 8 kg per ton of hot metal, and sulfur less than 0.061%, silicon greater than 0.42% is the boundaries of this study. We can say this is the outcome of the projects that we have discussed. And now there are two main ways to get titanium into the furnace. First, adding ilmenite or rutile to the burden. That gives you a slow overall hearth enrichment, good for prevention, but it's inefficient. Most TI end up in the slag and it can take weeks before levels in hot metal rise. Second, Tuyere level injection. Here you can target a hotspot, see a local effect within hours, and use less material for the same production. In these plant trials, discontinuous and high rate injection during tapping gave the best TiCN buildup. So this is very important outcome of this combined study. Now, from the multiple European campaigns, here are the key injection rules. Always inject at high hearth temperature. This increases TI in hot metal and reduces TI in the slag. Use discontinuous high rate injection rather than continuous low rate. Start mid or end tapping and stop after the tap hole closes. Inject upstream of the hot spot so the titanium rich hot metal flows past the wound area. For durable layers, inject for at least 1 week. Adjust injection to your base TI input from the burden. If drainage is poor, fix it before injection, otherwise TI cannot form the protective layer. So while applying, all these methodology are also to be looked into to enhance the effectiveness of precipitation of TiCN. In many of the blast furnace trials, the residence time of injected titanium dependent on Tuyere position also. For example, 90 degree from the tap hole, about it takes 3.5 hours. 180 degree if it is there, about 6.5 hours. So in Chinese trial, after starting TI ore addition, it took 6 to 7 days before the hearth temperature stabilized and about 10 days to get through the unsteady period. So we can say that 7 and 10 days band is good enough to corroborate our finding in terms of suppression of the temperatures in the critical area. Interestingly, during protection period, the fuel ratio actually dropped by around 5 kg per ton, possibly due to improved drainage and more active hearth condition. Now coming to our next slide, TiO2 is not a standalone cure. It works best when integrated with other hearth care measures, and these are also very important. Preventively, we aim for stable productivity. This is must, and typically around 2.2 tons per cubic meter per day is important. Coke quality, burden distribution, and keeping permeability high are the vital. Remedially, TiO2 injection is combined with gunning, a spray coating, or even a step replacement in some cases. And we must monitor thermocouple, head flux sensor, and occasional skull thickness mapping are all tools that tell us if the hearth is healthy or not. So now coming to the one more consideration, slag quality. If titanium in slag exceed 1 to 2%, cement producers may reject it because our major consumers are the cement producers. So we must have to be very concerned about the presence of TI. But the good news is even in aggressive injection trials, TiO2 level in slag stayed below this limit. Also, there is a byproduct opportunity. Titanium bearing blast furnace slag, our TBFS, contain around 20% TiO2. Recent work shows it can be processed into high value Ti5 Si3 alloy using molten salt electrolysis, turning a waste product into something valuable. To summarize, track your TiSi and sulfur. These dictate TiCN formation. Choose the right method, Boden addition for long-term prevention, Tuyere injection for urgent local repair, follow injection discipline, correct timing, Tuyere location and high heart temperature are essential. Monitor results and adjust daily. Finally, think long term. Combine TiO2 with broader health care practices to get the longest possible campaign life.